Okay, so the last section we're going to look at is 3.2, and it's on, as I said, three separate things: continuity, intermediate value theorem, which are kind of related, and then end behavior, which is kind of a separate thing. We're going to make a chart to talk about end behavior. We'll get to that. So when you draw something on the calculator, most graphing calculators assume that what you're trying to draw should be connected. So if you take an older calculator, like this one, and it turns on, and you try to draw the following. Okay, tangent of x. I'm going to do zoom 6. If you look at how it's drawing it, it's pretty bad. It shouldn't really look like that. What it should look like is this. Let me just clear that, and that too. Okay, let's do tangent x, and I'm going to do the same thing. Zoom, I did zoom 6, I'm going to do zoom 7 just to show you something. That's what it should really look like. Okay, it should have these curves to it, but it shouldn't be trying to connect. Oops, I didn't really want to do that. It shouldn't be trying to connect the curves together, which is what the older calculator is trying to do. All right? There's these what we call vertical asymptotes. Okay? And the calculator is trying to put those in, but it really should look more like what's on the left than what's on the right. Even on a newer calculator, if you go to Format, you can turn Detect Asymptotes off. If you do that, it's going to draw things a lot faster. Okay, so if you watch when I hit Graph, how fast it draws this time. That's faster. I don't know if you remember how fast it was the other time. But now it looks wrong. Okay, there's these vertical asymptotes that shouldn't be there. So if you're willing to sacrifice it speed-wise, it slows it down a little bit, but it draws it correctly. All right, so newer calculators can handle graphs that aren't connected. On a Casio, I'm not sure. A couple students, at least in my other class, have one. I don't know how it would do it. You'd have to check and see. All right, so let's try to graph this one. The graph of 1 over x minus 3. What value is not in the domain of f of x? How about Catherine?
3.
Which one?
3.
3, yeah, you can't use 3. So this graph is going to do something weird if you try to go to 3. Let's try and see. All right, it's heading towards 3. Whoa, all of a sudden it does that. So my question is, could you trace this entire graph, the whole thing you see on the screen there, without picking up your pencil? No, because they're not connected. This graph has 2 separate pieces to it. There's a word for that. Okay, let's look at this, integer function. Okay, the integer function looks like got a number int x. Looks like a series of steps. Could you trace all those steps without ever picking up your pencil? No, it has a lot of, and I'll tell you the term in a second. You have to pick up your pencil a lot of times to do it. Now, something like that, that's a parabola. Can you trace a parabola without ever lifting your pencil? Yes, because the parabola is connected. So the answer to the first 2 was no. The last one was yes, and that means something. And it has to do with what's called continuity. So we're going to use the words continuity, continuous, and describe a few different things. So we can say that a function is continuous on an interval. Okay, what an interval means is you're saying, okay, I want you to start here. Here's a value. I want you to end here. Here's another value. Can you trace between just those values without lifting your pencil? Okay. Maybe you can't trace the whole thing, but maybe you could trace between a small section without lifting your pencil. Right? So that's what I'm talking about here. Interval is a small section. So a function is continuous on an interval from a to b. A would be a starting value, B would be an ending value on the interval, if you can trace between A and B without lifting your pencil. Okay, it's not a super formal like math definition, but I think that makes sense to most people. I am going to define it a little bit more formally in a minute, but that's the basic idea visually. They tell you where to start, they tell you where to stop, and over that interval, the question is, can you trace from the start to the stop without lifting your pencil? If you can, that's called a continuous interval. If you can't, it's called discontinuous. So any questions on that idea? And there's different reasons why you might not be able to trace from point A to point B without lifting your pencil. Okay, there's really three main reasons why you would have to do that. And we'll talk about what those three reasons are. The reason that in f of x you couldn't trace the whole thing is a different reason than g of x. Okay, different reasons why you couldn't trace them without lifting your pencil. So it's possible that you could have a graph and you could maybe find certain sections that you could trace and then other sections that you couldn't. So you might have some intervals that are continuous and some that are discontinuous. So what we're going to do is we're going to look at exactly that. We're going to graph 1 divided by x. And I want you to name 2 intervals where you can trace between a starting and an ending value, and 2 intervals where you can't. Now, that's a pretty wide open question, interval. There's an infinite amount of answers to this question. The interval can also be open, it can be closed, meaning you could use brackets, you can use parentheses. It doesn't really matter. There's a lot of options. Well, let's draw it first and then see if we can figure it out. So 1 divided by x. That's what it looks like. Now, what happens is when it starts to get really steep, the calculator can't draw it anymore, but really, this should keep going down, and that should keep going up. So there's your graph. So when we name intervals, we're talking about x values. You tell me a starting x value, tell me an ending x value, and I want to see if I can trace between them. So let's start with a continuous interval. Can somebody give me an interval using an x value where I could start from and end, and I could trace between those 2 numbers without ever lifting my pencil? About Rob? Not sure. Well, let's look at the graph. So when we describe an interval, we're using x values. So, for example, if I wanted to start, I'll start you here. I'm going to have you start when x is 1. Could you tell me a number that I could trace to? And to do that, I would never lift my pencil. Two. Yeah, you could trace from 1, which is, if I make it bigger, it's easier to see. But if you start at 1 and you want to go to 2, mark where you want to start and where you want to stop on that graph. And now the question is, could you trace between 1 and 2? Yeah, you can trace between 1 and 2 without lifting your pencil. Now, it doesn't matter if you write the interval this way, or this way, or this way. It doesn't really matter. You can trace between 1 and 2. You can include the 1, you cannot include the 1, you can include the 2, you cannot include the 2. It's fine. But let's try something a little different than just 1 and 2. Could someone give me another interval that I could trace between the starting and the ending value on that graph? Oh, right? 8, okay. 8 to what?
4, I guess.
Well, if you're giving me, so you want 4 to be the first number?
Yeah.
Okay, so let's do it that way. So you want to trace from 4 to 8, open, closed, or half open?
Half open.
Half open, okay, so we'll go like that. You can trace between 4, which is right there, to 8, which is over there, without ever lifting your pencil. Okay, so there's an infinite amount of answers. Now, I'd like to name an interval that's discontinuous. Can somebody give me an interval that if you tried to trace from this number to this number on that graph, you'd have to pick up your pencil to do it? Yep?
-5 to 3.
-5 to 3. Again, it doesn't really matter if you include the -5 or not include it. The point is you could never trace from -5 to 3 without lifting your pencil. Could somebody give me one more? Yep.
-2 to 2.
-2 to 2. So we'll say -2 to 2. For this particular graph, what's the key? If you want to make sure you have a discontinuous interval, you have to pass through what x value? Yeah.
You want to have a negative.
Yeah, you want to have a negative and a positive. You want to try to pass through 0. Because passing through 0 is where you lift your pencil. So any negative number, any positive number, that's a discontinuous interval for this particular graph. So any questions on that? Yeah?
Can you do open, close, or half 2?
Yeah, it doesn't matter. It could be open, closed. You can include the 2, not include the 2. It doesn't really matter. Yep. So this graph isn't continuous everywhere, right? Because people gave me a couple intervals that are discontinuous. But it is continuous in some spots, all right? So some spots it is, some spots it isn't. All right, let's look at the step function again. So I'm going to put that back in. And it's called math number int. Okay, so here's my step function. I want to know, looking at that graph, what's the longest possible interval that you could find that's continuous? Let's just make it a little bigger. What's the longest interval on that graph that is continuous? How long is it? Yeah?
Like they're all the same.
They're all the same. And how long are they?
They're 1.
They're 1. Each one of those steps is 1 unit long. So the longest possible continuous interval you could find in the graph, in this particular graph, is 1 unit long. If you gave me a start point and an end point that was more than 1 unit apart, I guarantee your interval would be discontinuous. You can't do it on this graph. Now, if you go back to the other one, that's very different. The length of the longest interval on this one that's continuous, it's infinitely long. Because if you pick a start point here, you can trace all the way to infinity. So that one's a little different. Okay, but this one is a definite limit. 1 unit. So I told you there's a few different ways that a graph can be discontinuous. And we call that a point of discontinuity. The step function has a lot of discontinuities. Every time you lift your pencil to go up a step, that's a discontinuity. This particular graph has 1 discontinuity. at 0, okay, because you can't divide by 0. That's the only one in that graph. But even though they're discontinuities, they're different types of discontinuities. So you can get a discontinuity if you try to plug in a value that's undefined. For example, if you try to plug in 0 into a function, like this one, you would divide by 0. You can't do that. It's undefined. So when you draw a picture of it, you will have a discontinuity because the value is undefined. Another type of discontinuity, we call it a break. In the integer function, the domain is all real numbers. There are no undefined values in the integer function. You can plug in, remember, integer function says, you give me a number, and I'll give you the biggest integer back that's less than your number. So if you said like 3.8, I could say, okay, the biggest integer that I can think of that's less than 3.8, 3. 4.2, it would be 4. Okay. You can do it with positives, negatives, fractions, decimals. So there's no undefined values. It's just that because the integer function, it's almost like rounding. Your answers are integers. Okay, when you get an answer to the integer function, it could be 0, it could be 1. There's nothing in between. That's why it jumps up a step. So because of that, you have a break in the graph, and that causes a discontinuity. Okay, but it's not undefined. It's a break. And then the last type of discontinuity is the trickiest because you can't see it on the calculator even though it's there. Let's graph that. Let's graph x squared plus 3x plus 2. Okay, I'm going to put that in parentheses. X squared plus 3x plus 2. Okay, and I'm going to divide by x plus 2. So, if somebody were to walk in right now and they couldn't see the equation for that, and they looked at that graph, they would say it's a line. It's a line with a certain slope and a certain y-intercept. No, that's not a line. Because there's something there that's so small you can't see it. If you look at the equation, you can see it. What value are you not allowed to plug in for x here? -2. Now, wait a minute. There was a value we couldn't plug in here. It was 0. But when we graphed 1 divided by x, it was very obvious the way it curved. Right? We could definitely tell there was a break. Well, how come we can't tell there's a break here? Why doesn't it do that weird curve thing? Well, I can make it curve if I just change one number. Just change like a 2 to a 3. Watch how it looks now. Totally different. Now you can very easily tell there's a break. But why can't you tell when it was a 2? Anybody know why you can't tell? Yeah?
Well, mine came out to that when I put in like to the curve thing. Mine came out as a curve when I put in 2.
As long as you put parentheses like that, it should come out.
I put
You put the parentheses?
yeah.
And you had x squared plus 3x plus 2. Let me just take a quick look and see. No parentheses around the bottom. Yeah. So you gotta put parentheses around the top and the bottom. Alright, well, I could prove to you that there's a hole there, because watch what happens. If I type in -2, alright, press trace, and then -2, the y value is blank. There isn't one. Right? If I go to my table, and I type in -2, it says error. Now, if I go really close to -2, like let's go -2.000001. That's really, really close. No error. Works fine. Let's try -1.999999. Very, very, very close to -2. but it also works fine. Okay? Well, let's take the top and factor it. How does x squared plus 3x plus 2 factor? Yeah?
X plus 1.
Mm-hmm.
X plus 2.
Yes. X plus 1, x plus 2. The problem, or why this is happening, is because you have a common factor in the top and in the bottom. When you have a common factor, it causes it to basically cancel, and what this graph really looks like is this. It looks just like the graph of x plus 1, except there's a hole in it. Okay? So that's why it happens. When I changed the 2 to a 3, it didn't factor like that anymore. So the factors didn't cancel. So you get a hole in a graph when you have common factors in the top and in the bottom. And if you wanted to sketch it and really show it, you could go like this. Kind of exaggerate the size of that hole and then have it go on. Okay, but no matter how much you zoom in on the calculator, you'll never see that there's a hole at -2 because it's infinitely small. Negative 1.9999999 is okay. Negative 2.0000001 is okay. It's just at -2. There's an infinitely small hole. So if it's infinitely small, is it even there? Yeah. Don't think too deeply about that. Right. But that's the idea. Okay. So a little more formally, I could say a graph is continuous if there are no breaks, there are no holes, and there are no undefined values over a given interval. Which also means you can trace it without lifting your pencil. But the pencil thing is more just conceptual and it's easy for people to understand at first. But really, when you're talking about continuity, you want to use the big boy words. No breaks, no holes, no undefined values. Okay, one thing that's nice about polynomials is every single one of them is continuous. Lines are continuous, those are polynomials. Parabolas are continuous, those are polynomials. Cubics, they look something like that, those are continuous. You never have to trace your pencil. You never have to lift your pencil when you're tracing a polynomial. You'll never have a break, you'll never have a hole, you'll never have an undefined value. Ever. So if you have a function that's not just continuous over a small interval, but it's continuous absolutely everywhere. Like you can't find an interval with a break, with a hole, or with an undefined value, then that's called a continuous function. Continuous functions mean it is continuous absolutely everywhere. So all polynomials are continuous functions. Okay, and the idea that a polynomial is continuous from negative infinity to infinity, that's going to tie in with one of the other theorems we study, the intermediate value theorem. All right, it's intermediate value property. Let me just give you kind of an example first, and then I think the idea will make sense. Okay, let's say you had a pot of water, and in the pot you put water, and the water is at like 50 degrees. Okay, so the water starts out at 50, and you heat it up to boil. Right? So it started at 50, and you heated it. In Fahrenheit, boiling 212. Is there a time where the temperature of the water was exactly 100 degrees?
Yes.
Yes. Is there a time when the temperature was exactly 106.4 degrees? Right. How many temperatures does the water go through from 50 to 212? Okay?
162 temperatures.
Well, think about the temperature at one point could be 50.0001, 50.0002, 50.0003.
Infinite, I guess.
Infinite, right? It goes through all of them. Because this is what we call it's a continuous process. Okay? You're starting at a value, you're ending at a value. You have to go through every single value that's intermediate. You can't skip one when you're boiling water. It's not like you could be boiling water and if you had like a temperature probe in it and it graphed it, it wouldn't all of a sudden jump from like 80 degrees to 100. And what happened immediately and everything else? It can't jump, right? It's continuous, right? And that's the idea. If you have a process that's continuous and you have a starting value and an ending value, you go through every value in between, in every intermediate value. If you understand that, that's basically what the intermediate value property is. Right? So if you have a function that's continuous from A to B, so you can think of that as like your starting temperature for your water, your ending temperature. And we all agreed that boiling water is continuous, meaning you don't skip temperatures. You go through every single one of them. Then what that means is in this definition, your graph is able to take on every y value between f of a and f of b. So let's say a, you don't have to write down what I'm putting in red, but let's say that was the starting time. Let's say you started boiling water at 11 o'clock. And you finished boiling the water at, 11:10. So A is 11 o'clock, B is 11:10. So in our particular function, the value at 11 o'clock was 50 degrees. That's where the temperature started. The value at 11:10 was 212.
You wrote 11 again.
I wrote 11 again. Thank you. So the value at 11:10 was 212. What I'm saying is that if you pick a time between A and B, 11:03, 11:04, 11:05 and 12 seconds, whatever, if you pick any time between A and B, then I guarantee you at some point you will go through any number you want between 50 and 212. You want to go through 86.2 degrees, there's a time between 11 and 11:10 when the temperature was exactly 86.2 degrees. Okay. Any question on that idea? So you pick a value between 11 and 11:10, I guarantee you'll get a value between 50 and 212. Always. Okay. This is another way to say exactly the same thing. I think if I tie it in with the temperature thing, it'll make more sense. So this says basically pick a temperature between 50 and 212. Any temperature you want. I guarantee you I can find a time such that when you plug it in, there was a time between 11 and 11:10 when the temperature that you wanted was exactly what the temperature of the water was. Okay. So it's just another way of saying it. You can pick any number you want between f of a and f of b, which in our case was 50 and 212. And there's a time, there's an x value, somewhere between when you started and when you stopped, such that at that time, it's exactly the temperature you want it to be. Okay, as long as you pick a number between 50 and 212. If you pick 40, well, no, that wouldn't work, because we didn't start at 40, we started at 50. Okay, so let's look at an example that's not really a word problem with like boiling water or temperature. It's more just an equation and looking at the values of this particular graph. Okay, f of x equals 3x minus 4. What shape is that if you were to draw it? How about Justin? I think it's like y equals 3x minus 4.
It would just be a straight line.
Yeah, it's a line with a slope of 3 and a y-intercept of 4. Okay. So we know that lines are continuous. So I'm giving you a problem that applies. Okay, it's a continuous function. I want you to find a value between negative 10 and 10. Okay, an x value between negative 10 and 10, such that if you plug it in, you get 15 as the answer. First thing I want to do is determine if that's even possible. Okay, so let's start with our low value, negative 10. Let's plug in negative 10 to my function, and let's kind of see where the temperature of the water is starting. Okay, let's see what our y value is starting at. Then we'll see what our y value is ending at. And as long as it starts below 15 and it ends above 15, it'll hit 15 somewhere. So let's see. If we plug in negative 10, we're going to get 3 times negative 10 is negative 30 minus 4. So my y values are starting at negative 34, and they're ending at 3 times 10 is 30, minus 4 is 26. So for my range, I'm starting at negative 34, I'm ending at 26, and we're doing it on a line. A line is continuous. No breaks, no holes, no undefined values. So am I, at some point, going to pass through 15? Okay? Yeah. If I'm starting at negative 34 and ending at 26, I'm definitely going to pass through 15 somewhere. Now the question is where? What value between negative 10 and 10 would it be? So we're solving for a value you plug in for x that makes y 15. So just plug in 15 for y and solve it. And we're guaranteed we're going to get an answer between negative 10 and 10. Let's see what it is. So we get 19 equals 3x divided by 3. Right there, 19 thirds. So it's just 6 1/3?
Yeah.
So 6 1/3 is the x value that you could plug in between negative 10 and 10 and be exactly at a y value of 15. That's kind of like the time in the boiling water problem. That's the time when the temperature is 15, if you want to think of it that way. Okay. Any questions on that? So mathematically, it's not really hard, really. You're just plugging in a number here and solving for x. But I want you to understand the concept of continuity. Okay? Even though the math itself isn't that hard. Okay, so this is a parabola. Okay, let's graph it just so we can look at it. X squared plus 3x minus 4. All right, so x squared plus 3x minus 4. Okay, so what I could do is I could limit my window. Okay, I'm only looking between negative 2 and 3. So let's do that. Between negative 2 and 3. That's it. Pretend that nothing else exists except what you can see on the screen right there. Just that part of the parabola. So, the question is, can we find a value somewhere where the graph hits negative 3 with what you can see on the screen? And if you look, of course, if you draw a horizontal line, position it at negative 3, see if it hits the graph somewhere. 1, 2, 3. Yes, it does. So there is a spot where we would hit negative 3. I want to find that spot. Okay. If you weren't sure. You're like, well, I'm not really sure. Oh. If you find that value, plug in -2. I get, let's see, what's that? 4 minus 6 is -2. -2 minus 4 is -6. So I'm starting at -6, and I'm ending at 9. 3 squared is, 3 squared is going to give me 9, plus another 9 is 18. 18 minus 4 gives me 14. So my y value isn't actually high enough. I should set it a little higher, but I'm ending at 14. So the value that I'm trying to go through in the middle is -3. Yeah, -3 is in the middle of -6 and 14. So you'll hit it somewhere, as long as your graph is continuous. Now, if that was a step function, I can't guarantee anything, because you're picking up your pencil all over the place, but you're never lifting your pencil here. Okay. So let's find it. Where would I plug in that -3? About Emily?
We would put it where the f of x is in the original.
Yeah, we're going to plug it where f of x is, because we're trying to find a value for c, so that when you plug it in, right, in place of x, you get -3 for the value. So let's try that. So -3 equals x squared plus 3x minus 4. Now you could solve that using factoring if it works, quadratic formula, or completing the square. What I'm going to do is just this time use the calculator, put in a value at -3 and see where I hit it. Okay, I hit it right there. Second calc, intersect. Because I didn't get a nice answer for x, probably doesn't factor very nicely. So x is 0.303, or actually c. C is the value you could plug into the function, and when you do that, you'll get -3. Any question on that one? Now, just because, let's say, I don't know, let's say you had something like this. And I said to you, all right, you're going to start here, and you're going to end here. And let's say that this was at a y value of, I don't know, 4. And this point was at a y value of 6. At a minimum, I know I'm going to go through every y value between 4 and 6. But if you look at these lines I'm putting in, okay, I'm guaranteeing I'm going to go through everything between those lines. But I might even go through more. Okay, and I do. I actually go much lower than 4. Okay. So just because you check a starting value and an end value, you're guaranteed to go through the y values between these numbers, but not necessarily only those numbers. You might go through even more. Like this graph dipped down lower, and it dipped up even higher. So maybe you go through values as high as 12 and as low as 0. Okay. We didn't check for that, but that could happen. Any questions on that idea? That you can go through more y values than just what your starting point and ending point are? What kind of shape would that wouldn't happen, what I just said? Like if you had a starting y value and an ending y value, that would be it. Those would be the only y values you ever go through no matter what. Yep. A straight line. Yep. If you've got a starting value and an ending value, there's not going to be any funny twists or curves. You're guaranteed those are the y values and only the y values you're going to go through. Yep. this one. This one, I want you to prove to me that if I graph that function, x to the 5th plus 2x minus 1, that at some point between 0.25 and 0.75, I will cross the x-axis. Or there will be a root. Or there will be a 0. All the same thing. Prove to me that at some point between 0.25 and 0.75, I find a 0. Right, so x to the 5th plus 2x minus 1. That's a 5th degree what? What kind of graph is f of x? It's not going to be like a super specific name. It's just a kind of a general category. Yep. Not that general. But yes, I agree. It is a function. We need to be a little bit more specific because this is also a function, but it's not what that is. Yep. It's a polynomial. That's the key. All right. So f of x is a polynomial. And what do we know about polynomials when you draw them? Any polynomial. Yeah.
They're always continuous.
They're always continuous. That's the second thing that's important. Polynomial functions are always continuous. So how could I prove that somewhere between here and here, you're going to pass through 0? What would I have to show? Yep.
Would you have to show where that line intersects the x-axis?
We're not going to use a calculator. Yeah, so we're not going to use a calculator at all for it, since it's more of a proof. So what does it mean if your graph hits 0? What does that mean again? What's another way of saying that? About Joe? I said all three of them right as I was reading this question. I said, prove that there is a 0, which means this, which means that. What's one of the other ways I just said you have that's equivalent to that? If you have a 0, that means your graph is doing what? It means there's a root. That's not the one I'm looking for. It's the third one. What's the other thing? Like if someone said to you, I have no idea what you mean when you say there's a 0. Can you describe to me what that would look like when I draw the picture? What would you say to someone who's looking at a picture? You'd say, here's the 0 because look at what the graph is doing. Yes? Close. It's crossing what? The other one? Which one? The x-axis. The graph is crossing the x-axis. So what happens to the y value when you cross the x-axis? It goes from what to what? It goes from positive to negative, or negative to positive. So if you can prove that at this value, your graph started out in the negatives, and when you ended, your graph was at the positives, then if you went from negative to positive, and you never lifted your pencil because it's a polynomial function, you must have passed through 0 at some point. This question's not asking where do you pass through 0, just prove that you would at some point. So let's write it out and show you know kind of what you have to do, but I pretty much just told you. So since f of 0.25 is, now I need to know what that is. So let's check it. Sometimes I might use the graphing calculator, but I can probably check it just as fast without even graphing it. Just 0.25 to the fifth, not squared, 0.25 to the fifth, plus 2 times 0.25 minus 1. Minus 1. So, since f of 0.25 is a negative value, I'll just write what the value is. Since f of 0.25 is negative 0.499, and f of 0.75 is, this is where if I had to keep doing these over and over, it would be much faster to use the table. But since I only have 2 of them, I can just type it in. So plus 2 times 0.75 minus 1. And f of 0.75 is 0.737. My y value went from a negative to a positive. My y value went from negative to positive, and this part is the important part, on a continuous function. So my y value went from negative to positive on a continuous function. This means I have to pass through 0. There's no way to go from negative to positive without passing through 0. You have to. So this means you must pass through 0. So what we just did is use the intermediate value theorem to prove that you had to pass through a specific number, the number 0. In fact, I guarantee you'll pass through every y value between negative 0.499 and 0.737. In particular, you're going to pass through 0. That's the one I was interested in. Any question on how we tied the idea of continuity and intermediate value theorem together in that problem? Okay. So that's the first 2 things. So those are probably the hardest ones, the continuity and intermediate value theorem. So the last thing is basically telling me how you could give me any polynomial, you could give me any exponent you want, and I can tell you exactly what it's going to look like in terms of its end behavior. If you said to me, well, graph 5 times x to the 205th power, I know it's going to look something like this. I can't tell you exactly what it's going to do in the middle, but I can tell you if I graph 5 times 200, I don't know what I said, 6 to the x to the 205th power, it's going to go up on the right, it's going to go down on the left. I know. So, how do I know that? That's what I'm going to show you. So, the end behavior is basically what's happening on the ends of the function. Not the little twists and turns and curves in the middle, but what's happening when you head very far to the right and really far to the left. Let's look at this one. Y equals x cubed. Let's graph it. So it's the parent cubic function. Not the best window, but good enough. You can see that it's going down on the left, it's going up on the right. So there's a couple ways we can describe what's happening here. Let's start by describing it this way. Okay, on the right-hand side, this is called limit notation. You're basically, if I read that to you formally, exactly the way it's written, it says, what is the limit of the limit of f of x as x approaches infinity equals, and the bottom one says the limit of f of x as x approaches negative infinity equals. If I attempt to translate that into something clearer, what's happening to, or what's y getting closer and closer to as x gets bigger and bigger? What's y getting closer and closer to as x gets more and more negative, smaller and smaller towards the negative direction? So let's look at it. Looking at that graph, as x gets bigger and bigger and bigger, what's happening to my y value? Yeah.
It's increasing.
Increasing, and what's it approaching? Infinity. Yeah. As x gets bigger and bigger, so does y. Just check the table. If x is 10, we're at 1,000. If x is 500, we're much bigger. So as x gets bigger and bigger, y keeps getting bigger and bigger. What about as x gets more and more negative? What's happening to the y value then? Yeah?
It's also getting negative.
Yeah. As x heads further and further and further to the left, y heads further and further down. Never stop. So what I just described there, that's called limit notation. That's more the big boy way to describe it. This is kind of another way to describe it, but it's not really used as much. It's like a set of parentheses and you put arrows. So this particular graph, down on the left, up on the right. Down on the left, up on the right. So looking at that, knowing that this first arrow could point up or down, and the second arrow could point up or down in other functions, that gives you 4 different types of end behavior. You could have both ends up. Can anybody think of a graph where both ends point up and up? Yep. And what's that? Yeah.
Is that a parabola?
Yeah, we're on the right track. Yeah, it's a parabola. So parabola, up, up, or if you flip the parabola over, down, down. Or the kind of graph I just showed you. One end goes up, one end goes down. So this one, bless you, would look like that. This one, more like that. Now, I'm not saying that it can't twist and turn in the middle. I mean, it can definitely do something like this. For our purposes, that's the same thing. Up on the left, down on the right. Bunch of local extrema, mins and maxes in the middle. But that's not really what we're focusing on. We're kind of looking at the big picture. Okay, what's happening on the left and right. So, let's look at a chart that summarizes, just by looking at 2 things, what the end behavior is going to be. So, if you had, did I put it down here? No. Right. This is your leading term. Okay, so you might have like 8x to the 5th minus 2x cubed. Yeah, all that other stuff after 8x to the 5th, yeah, that's great, but it doesn't really matter. The leading term is the only thing that matters. And there's 2 things you look at. Look at the coefficient, and you're going to ask yourself, is it positive or negative? Is it greater than 0 or is it less than 0? And then look at the exponent. Is the exponent even or is it odd? Those 2 things are all you need to know to figure out end behavior. If you have a positive coefficient and an even exponent, let's say something like this, 2x squared, the end behavior is up, up. If you had a negative coefficient and an even exponent, negative 3x squared would be down, down. if you had something that was, let's look at this case, a positive number in front and an odd exponent, 8x cubed. It's going to look something like that. Down on the left, up on the right. Throw a negative number in front of something with an odd exponent, it's going to look more like this. Okay, I'm not saying I'm getting the middle exactly right, but the end behavior is right. Okay, so any questions on the two things you have to focus on? Number in front and the exponent. I already said all of this. So all you're looking at, this is what I thought I had earlier. You're looking at the leading term. It's the term with the highest exponent. That term completely controls the polynomial. If you've got other stuff after it, great. But I could erase or change anything I want right there, and it wouldn't affect the end behavior at all. Might affect the twists and turns in the middle, like the fine details, but it's not going to affect the end behavior. So all you have to look at is the leading term. Any question on that idea? Okay, so to say it another way, if you've got some really long polynomial with a bunch of stuff, just look at the first term. Determine if the coefficient is positive or negative. Determine if the exponent is even or odd. You can ignore everything after it. And the thing that I just circled, that a sub n times x to the n, we call that the end behavior model. That's the, I'm going to abbreviate that EBM from now on. So if I went back to this one, and I asked you for the end behavior model of what I have in red at the top, you would say 8x to the fifth. That's the model that predicts the end behavior of that function. Okay. So the EBM is just the first term. Forget everything else after it. Okay. So any question on end behavior model? Alright, so what I want to do is graph something and show you the difference between the original and then just the end behavior model. And watch what happens. So if I graph 2x cubed minus 7x squared minus 8x plus 16. And then I graph 2x cubed. Let's see, the first window they tell me to do is negative 8 to 8, negative 100 to 100. All right, so they just picked that for whatever reason. Negative 8 to 8, negative 100 to 100. Okay, and hit graph. What you're seeing right now, that's the original. So what you're seeing in blue is the original. What you're seeing in red looks different, right? Do they look exactly the same? No. But that's because we're zoomed in and we're looking at the detail, right? Let's zoom out even further. So let's go negative 40 to 40 and negative 10,000 to 10,000. Now let's look at it. So now we're not looking at the detail, we're looking at the big picture. So there's the graph in blue with all the minus 7x squared minus 8x plus 16. And there's the graph in red. How do they compare now? Well, Tori? Just Yeah, they look almost identical because 2x cubed is the EBM. It's the end behavior model. It predicts what the graph is going to look like if you look at the big picture. That's all I'm trying to show you right there. Okay. Can somebody tell me what the end behavior model would be for this one? Like the one thing that I could graph that would show me the big picture. The details would be different, but the big picture would look the same.
Negative x. Oh, no, sorry. Negative 0.5x to the fourth.
Negative 0.5x to the fourth. Perfect. So that's the end behavior model. Now they want to know the specific end behavior. So this is a negative number in front, even exponent. We can do it as the arrows if you want. What's this graph going to look like on the left and on the right? Just want to know up or down. Yep.
Down.
Down and down. This particular graph is like an upside down parabola. Okay. Any questions on that? Okay. And no, that's not worried about that one. Okay, so that's the homework for tonight. So it's on 161. Okay, 1 through 6, 9 through 12, 15, 16, 21 to 25, 29 to 31, and 33. Okay, I will be after school today. If anybody needs extra help or needs to take a test, we'll go over that first thing tomorrow. And then we have our last test before progress reports tomorrow.